In this video, we're going to focus on digital design and using building circuits basically that use digital circuitry, gates, basic gates like AND, OR, and exclusive OR. The assumption in this video is that you have some familiarity with binary logic and you have some familiarity with the basic gates such as AND, OR, NOT, and exclusive OR. And also, the other assumption is that you've had a chance to take a look at a video that is online at YouTube, which describes basically how to log into TinkerCAD, because that's a medium we're going to use, and how to create a design there, and how to use some of the basic tools, as placing components, as well as power supplies, voltmeters, multimeters in general, and things of that nature. So if you've done that, now we are ready to jump in and start exploring some of the digital logic circuitry that we need to do our work. So let's go ahead and start by just creating a new design, new circuit. If, by the way, you're here and you don't see the title circuit in here, all you have to do is click on the circuits, and that's the electrical portion of the TinkerCAD, and it brings you up to here. You can either create, by clicking on this one, create a new circuit, or I have a test one sitting here, so we'll just go there. If you already have a design you're working on, it'll save it automatically, and you can come back and basically tinker this, which means go ahead and work on it. I don't think there's anything in here, it's completely blank. If you recall, the components are all on the left-hand side. You have a little bit of an option of how you organize them. You can do them one in a row with the description of each items, or if you know what they are, you can double them up so you can see more of them. One of the other things it does is that as you use the components, the more frequently they keep coming up on the list. So the more you use them, the earlier on the list they'll show up. This is the basic list. It doesn't have all the components in it. If you want all the components, then or all the tools that are available, you just select all, and that brings it up. Let's go. The first thing you want to do when you're doing a design, of course, is to go find a proto board and put that proto board. So I'm going to use this big proto board, and as you know how we use it is when you click it here and then position it where you want on your board, and there it is. And as soon as you position it, it gives you a property sheet up here, which basically for every component, it shows you all the items you can change. For a proto board, the only thing you can change is the name. So proto board, okay? And it looks like it's running a little bit slow on this one, so we just let it do its thing. Typically, it's pretty good speed, so I'm not exactly sure what's going on here. So as you recall, and then if you've forgotten how this is connected, you just go over each hole, and it tells you that all of these holes in this horizontal line are connected to each other. These are all connected to each other, and if you come over here, notice these are connected together like that. So that's basically what it, and the reason we have a proto board is there's a couple of things. It gives us a hard place to put the component to hold them in place, and it gives us a way of quickly connecting two things together. So if I want to connect two things, I put pin for one in here, put the next one in here, they automatically are connected. I don't have to twist them together or use an alligator clip or whatever else I want to do to make that happen. And also the holes are spaced such that they allow us to use like resistors, capacitors, LEDs, and just push them in. The pins are the right size at 0.1 inch to accept all that. And also they're designed so the gates that come in what we call chips, they come dual inline package, which means there are basically two long rows of pin on them. It allows them to be placed in there very nicely. Let me go ahead and grab one of the, here we're gonna play with some of them, and let's go ahead and start, for example, for 74 HC 08, which is a 2-input AND gate. Now notice that the middle two digits here are HC. If you worked in one of my labs or our labs, you will see that we use LS. LS just just the technology used to produce the two input gates. HC is typically faster, lower power. LC is a little older technology, but one of the advantages it has is less sensitive to ESD. ESD stands for electrostatic discharge. So whenever you pick something up, your body has a voltage that carries with it. And in some dry weather, if you're walking on a carpet or whatever, you could be carrying up to about 1,000 volts of static electricity, and you could damage the part. LS, if the middle two digits are LS instead of HC, they are much more able to handle that than HCs. HCs are a bit more sensitive to that. There are many other differences between the two, but for the purposes of this discussion, we can pretty much treat HC74HC08 the same as we treat 74LS08. As a matter of fact, when I'm showing you the data sheets, I'm going to go to the LS because I have them all collected in one place. But you can always Google these and find out what the data sheets for these one says. But okay, so that's that. So let's go ahead and bring this in. I'm going to just click on this and bring it in and put it someplace. This is a good place to put it, okay? I might want to take this one up a little bit so I have room to put some power source in here. So maybe in the next, remember these chips, in order for them to operate, what do they need? They need a +5 and ground. How do I know that? Well, the reason I know that is because I go on Google and search for, in my case, I'm searching for 74LS08, but they have about the same pins. And the 08s are, the LSs have better data sheets showing the pins a little more clearly. So here is an AND gate, for example. This is called a quad AND gate. So I've got 4 of them in here. Here the input is pin 1, pin 2, pin 3 is the output. Here's what it does. Of course, my assumption is that you know how an AND gate works, so I won't go through this basically. And here is the low, and by the way, low, 0, high, 1 are the same thing. High and 1 are the same thing, or sometimes we call true as well, shown with T. Low, 0, and F as false are also the same way. Depending on what data sheet you're looking at, they will use one of those 3 schemes to indicate the logic for you. And as you've already in the text material or other places you've covered, you know this is called the truth table, where we show the relationship between input coming in and the output going out. So in this one, we see that the input comes in pin 1, second input comes in pin 2 for this gate, and output goes on 3. And then before this thing can operate, pin 7 and pin 14 has to be connected to +5 volts or VCC, and 7 has to be connected to ground. So let's go back here and see how we do that. So where am I going to get my power from here? I need a power source. So either I can go back here and look at everything and just walk through it, or I can just say I need a power supply and see what comes up. Here is a power supply. So I'm going to take my power supply and maybe put it right here. So this, actually, let me put it in one corner so it's not in our way, okay? And so typically, let me take a look. So it basically said, well, you can be nice and call it VS or some other than 1. If you have multiple power sources, you could have different names for them. This one says the voltage is set to 5 and the maximum current is set to 5 amp. Sounds great to me. Let's go ahead and do that. And by the way, it's really nice if you connect the chip incorrectly to this, it'll show you a little red star on it, kind of blowing up and say, hey, you got a problem, and it shows you what the problem is that you have. As a matter of fact, let's go ahead and do that. You have this thing set at 5. Now, as you can see on here, there is a dot over the pin 1. So this is pin 1, this is pin 7, and then you see this little notch. Sometimes they don't have this white dot on it, so you got to kind of zero in. There's a little notch here. It's kind of hard to see. So that would tell you that to the left of that notch is pin 1 through pin 7, 8 through 14. It's important for you to remember. And this is kind of nice. This tool tells you where the power goes. And then I go over the cursor, and it tells you where the ground goes. All right. So so another general thing we do with prototype boards is instead of going from power supply directly to each component. We could have 30, 40 components in here. We don't want to draw a wire always from the power source to it. And if you recall, these pins are all connected. And if you see, there's a plus sign next to it. And these pins are connected, there's a minus. So it's probably a good idea to click here, take a wire, and connect a wire to this pin. And it would be nice if you color coordinated. For example, all the grounds are black typically in digital circuits, and all the plus are red, so we just say red, okay? And then now the power and grounds are all on these pins. Once in a while, they like to do, you know, sometimes we also want to have power and ground on both sides. See, so regardless of whether I want power this side or this side, I don't have to go over the chip. And again, this is not necessarily for this. This is just a good idea for what you could do. So I can basically draw a wire from here to the plus here and make it red so we know it's power. So now power is here and power is here as well. Then what I could do, I could also take another wire from here and take it here. So now I have ground on the other side as well, and I'm going to make that black. Now my proto board is set up to have all the power and ground that I need to make this thing work. Great. So in order for the chip to work, I have to have one pin connected to ground, and you got to be very careful to connect it correctly. So hopefully I did. If not, the chip will kind of virtually blow up and tell me I connected it incorrectly, which is really, really nice, because in real life, you basically damage the chip. So even though you can kind of play around with it here, when you're actually building it in the physical world, you got to be a little more careful. Okay, so I've got the power and ground. Basically, I've biased the chip. Now I'm ready to use it. If you recall, pin 1 is ground, and pin 1 is one input, pin 2 is another input. So now I'm going to try to build a switch. So if you remember how the switches are built, we need a switch. One side we need to have a pull-up resistor. The other side we got to have it ground, and then we got an input. So let's go ahead and try to find a switch. I don't know where they are, so I'll just say, okay, do you have a switch that I could use? I'm not sure where I'm typing, so let me see where I'm typing. I somehow started a simulation. Let me stop that. I'm not ready for that. So let's go ahead and say, okay, I want to switch. Must not be. There's a switch. Okay, I'm only going to have 2 inputs. So let's go ahead and grab this switch and put it somewhere here. So when I put it here, what happens is these pins are hooked up this side and the pins are hooked up this side. I now need a couple of resistors for my pull-up resistor. Oops, resistor. There is my resistor. And I'm going to take one. And notice I'm just not going to use wires. I'm just going to drop it here. And then can I copy so I can get another one and put it here. So now pin 1 and 2 are going through the resistor to VCC. All I have to do is get a P wire from here, drop it to ground. Oops. And then drop it to ground. So, and I'm going to go follow my advice and make sure these are all black. So it's, you know, when you're debugging, this is a simple circuit, but when it gets complicated, it's kind of hard to figure out what you need to do. All right. So now what I've got is, I've got this thing set up, and I don't know what happened to my power here. I thought I had it connected to power. Maybe I removed it. We'll just say red, so put it back on. All right, great. So now we have this thing set up, 2 inputs coming from here. So when the switch is turned to on, this switch is closed. On means closed, so it's connected to ground. And then when it's open, it's connected to a pull-up resistor. So when it's on in this current position, you see a 1, and when it's in the on position, you'll see a 0 from here. But if you haven't studied, you got to go back to the text and kind of review that as well. All right, so we've got our switches set up, our inputs set up. So all we need to do is go ahead and take this input, come back down. Oops, I didn't want to do that. So let me remove that. And I'll keep all the signals in green. There is one, and then there's the second input. And then I want to know what's happening on my output. And typically in digital design, we like to use, I'm going to put this, whoops, I don't want to put it there. So let me move it just a touch up. Oops. Okay, so this resistor is connected to ground, and I want to use an LED. So I'll just say, okay, oops, I don't want the code. I want to use LED. So I'm going to use an LED. Here is an LED. I'm going to grab it. And I always forget which side is which, but it's really important. You see one side is tilted, one side of this LED has a little bit of a bend. So LEDs only can carry signals from one side to the other, only in the forward direction. And in order for you to turn this on, you have to have a higher voltage on this side. So what I'm going to do is take a piece of wire from output. Remember pin 3 is the output, and I'm going to take that to the pin of the LED. So if everything works, we should be able to have this LED turn on when we do the simulation. So if you remember, just like the electrical side, the analog side, if you want to figure out whether this is working or not, you just basically start initializing, and you see both of these switches are down. Remember, this circuit is open, so this is directly connected to 5 volts. And if you go back to the data sheet, it says when both are high, you get a high. That looks great. So if one of them goes low, then the circuit will shut down. So we're going to go over here and close the switch, which means now this wire is connected directly to ground. So you got a 0 coming in. 0 and 1 gives me a 0, and I got light off. Okay. Now let's just take this to the next steps. It's okay. That was great and everything. So stop simulation. Let's see what other chips are available in here. So I think I could just basically give it a partial list. And all the parts in here, all the parts in here are all the digital parts in here are 74. Let's see if they have, no, they don't have HC. So let's see what we got. So let's go ahead and replace that with this was an AND. Let's replace it with an OR and see how that works. So an OR would be this one. I'm going to bring it here for the time, leave it here for the time being. I'm going to take this guy and move it out of the way and see how it's going to behave if I take an OR and place it, hopefully place it in the right spot. There it is. So I'm going to go back to my trusty GRCS component side and say, okay, let's go ahead and see what a 32 is. A 32 is a 2-input OR gates, which basically says, okay, same, you notice the inputs are in pin 1 and pin 2 for the first one. The second one is 4 and 5. We're just going to focus on this one for now since we have it set up. So in this case, it says, oh, it's an OR gate. An OR gate, if either one of the inputs is high, the output is high. So let's see if that's how it works. So we're going to go back to our circuit here now that we have the OR gates in here. And we're going to say, okay, let's see how it operates. So if let's make put both of them to 0. Remember the switches. Oops, I did not want to move the switch. So let's go ahead and start the simulation. And so we both put both of them are 0. Now the switch both are closed, so 0 is going in. 0 and 0. The light went off. If you notice the light here, hopefully you can see it. And then now when I turned one of the switches to a high position, open the switch so it's not connected to ground anymore, I see the light turn on, and you can see if turn both of them on, if this is go, as long as one of them is open, the value is high, the light turns on. So this was a bit of a overview of the chips. And by the way, the only other one we use in some of our labs is 86. which is a exclusive OR, and the only thing exclusive OR is different from these guys is that the output is only 1 when inputs are different. If one input is 1, the other one is 0, you get a 1, otherwise you get a 0. And again, here's the data sheet. Very, very consistent format. The data sheets are pretty consistent. That's why I like these data sheets. And again, once again, LS and HC are talking about high-speed CMOS technology and low-power Schottky technology. HC is a much newer technology. It's much better for everything you want to do, except for sensitivity to electrostatic. And since we are in the lab handling it quite a bit in most of the educational lab, we'll try to use LS parts. Okay, so here's an example of, here we went through of building this. Now you should be able to build whatever logic you are able to design. You can put them in here, test them, see if they behave the way you think they should. Thanks again for watching, and look forward to seeing you in the next video.